So to wrap up this section, hopefully, we're going to do this. Well, now that we kind of have wires, we have resistors, right? How do we do some calculations with it? How do we figure out something that's a little bit more complicated than just one wire, one resistor? Okay, we can start constructing some circuit that has a voltage supply to it. A lot of times this will be named power supply. They're the same as each other, even though they don't exactly mean the same thing. So when we either say voltage supply and power supply, especially in this class, these are going to be a constant voltage supply. Okay, and these are usually drawn with two long lines, one short line. And in your introductory class, they may call this a battery or an EMF. Okay, so this is a voltage, supply. Let's call it S. Okay, and let's say I connect this to a resistor with some resistance R, and I just connect the other end back to the negative end of the voltage supply. So this is the positive end, this is the negative end. Okay, so this constructs a circuit. So what happened is that current, positive charge, which is what current is, right? Where the convention is that we're tracking how the positive charge is moving. What's in reality is actually negative charge is moving backward along it. So these charges are moving from your battery through the resistor, and this resistor is dissipating some power from it. It's just heating up. Okay. All the carbon film resistors we have, as long as the power dissipated, DSS is around, well, actually less than 0.25 watts, then you're okay. Because usually what happens is that the heat just kind of goes in the environment, and it's not going to cause a fire or something like that. Okay, so this is a way to draw a little circuit where you have a power supply and a resistor. Okay, another way, which is what you're going to see a lot, okay, is that you're going to have some V supply here, and it's just going to be a dot, and you're going to have a resistor in it, and it's going to go like this. Okay, so this little symbol here is considered the ground symbol. Okay, so this is the same. These two circuits are exactly the same. Okay, where V supply here is basically whatever the supply voltage is. Let's say it's 5 volts, and then you consider every point from here up to the resistor at 5 volts. Okay, anything after resistor is actually considered 0 volt potential. Okay, and therefore, right, so you still have the same delta V of 5 volts across this resistor, just like if you have a 5 volt battery here, right? You have a 5 volt difference between the resistor. These are exactly the same circuits drawn slightly different, and I don't want people to get confused by this because it's showing the same information. A lot of times this is more useful because what happened is that you're going to start connecting other things to this, and then anywhere that's ground, you want to just connect the ground to it. Anywhere that's 5, you can connect the 5 to it. This is usually more useful schematically, but this version on the left here is a lot of times more useful when you're doing Kirchhoff's law and doing loops and stuff like that. It's easier to think about. So that's why we keep them both. Okay. So a way to think about electrical current is just think about it as kind of like water current, because you can physically see water flowing. So let's say you have a little river, right? You have some water flowing through it, and then it reaches some lake, right? Some reservoir. And let's say, the current is flowing in this direction. I'm not even going to put a symbol there yet. But then out of this lake, there's actually 2 rivers that flows out of it. Okay. Okay. I'm going to call this I1. And then let's say the water is flowing out of these 2. Let's call this I2 and I3. Okay. And these directions are going to be important because it kind of shows you the direction that the water is flowing, right? Right? So if the level of the lake stays the same, whatever water flows in here, right, has to flow out, right? Because otherwise the level will start rising or dropping, because if you have too much water flowing in or out. Okay, so already you can actually see this is actually Kirchhoff's law. So, you know, if you were around in the 1800s, and you think, oh, well, river flows in, water flows in, water flows out, you would have a law, a physical law named after you. So basically what happens is that I1 has to equal to the sum of I2 plus I3, right? So another way to write this is that, well, this is all the current, that is sum of the current that is flowing into your lake, or your, in this case, in electrical talk, it's going to be called junction. That's the equal to all of the current that's flowing out of your junction. Okay. Okay. And this is basically Kirchhoff's junction law, current law, okay, which is actually written down here. Okay. To deal with the voltages, okay, and this is where the loop version of something happen of some of this is useful. So I'm just going to redraw that down here. So let's say you have some voltage here, some voltage supply, and then you have, I'm going to do multiple resistor just to make it a little bit more fun. You have some resistor 1 here, you have some resistor 2 here. Maybe you have another voltage supply that's actually backward on here. And then you have some resistor 3 here, voltage backward. Okay. What happened is that the way the book describes it is that the sum of all the EMF, meaning all these voltage batteries, equals to all the voltage change across it. The way I like to do this is actually to think about, okay, if you go around a loop like this, okay, the change in voltage across the loop has to be 0. And hopefully this will make sense, because let's say I start off at this point A here, right? If I travel across this, I gain Vs amount of voltage. Okay. If I go across this resistor, I actually loses a delta V across that resistor. I go across this second resistor, I actually drop another resistance. And in this case, now I'm here at this point, right, before battery B. Okay, since I'm going across this battery backward, okay, in the wrong direction, I actually lose voltage of battery B. Okay, and then now I'm at down here. I'm going to travel across this resistor 3, and that's going to give me a drop in resistance, drop in voltage across this resistor. And now I'm exactly at the same point. If you're back at exactly the same point, your voltage better be the same, right? Because you're literally looking at the same place. Okay, so all of this turns into 0. That's the way I like to think about it. So this is actually from my general physics textbook, where this one is from Steck. So you can use whichever one you want, but I think, to me, you know, there's literally no memorization, at least for me in my version, because, well, I start off at the same place. I start off at point A. I ended up at point A. The voltage there better be the same, and that's all I have to think about. And then, you know, the Kirchhoff's current law, right? Also tells you, just, you know, imagine a river, and then you figure it out. So none of this should require a lot of memorization. Okay. So, and this is probably more of a general case where you have just delta V of devices. Okay. So let's do a quick little example where we have some voltage source, VCC, and let's say VCC is at 5 volts. And then we have some resistance. And the first one is 25, the second one is 50, the third one is 100. So you have 25 ohm, 50 ohm. We have 100 ohm here. Okay, and we just want to calculate the power that is dissipated by each resistor. Okay, how do we figure it out? So the power dissipated by a resistor, the way I like to write this is actually PIV or PIV, right? So that's the easy way to remember that equation. So in order to calculate this, I have to figure out, well, what is the voltage drop across each of these resistors, right? Because this is per resistor, right? Okay. In order for me to do that, I have to figure out the current. I have to figure out the voltage drop across each of the resistors. Well, one thing is that the current is actually the same, right? So if you imagine a little river here of water flowing through this resistor, and whatever water comes out of here has to flow through this resistor 2, has to flow through this resistor 3. So all three resistor actually has the same current, right? I'm just going to call that I, right, without the subscript. The voltage drop across resistor 1, right, is going to be different than the voltage drop across resistor 2, than resistor 3, because each of them has a different voltage across it, right? So different resistance. So, but according to Ohm's law, this is just going to be I, right? Because it's the same current, and times R1. This is going to be I times R2, I times R3. And we already know all these three resistance. The only thing we're missing is actually the current. So how do we calculate the current? This is where we can do a little bit of analysis to make things a little simpler for us in the future, because these resistors are actually in series. So hopefully this sounds familiar already. Okay. So if you have, I'm going to derive the 2 resistor case, and then you guys will derive the 3 resistor case in the homework. So the 2 resistor case is that, well, if you apply a voltage across both of these resistors, what is the equivalent if they were just combined into a single resistors? And obviously the book already wrote the answer down, which is just going to be R1 plus R2. Okay, but let's just see how we derive this before we use it. Okay, so let's just do this with the 2 resistor case. Okay, so you have some voltage A here and some voltage B here, right? And we know the current between them has to be the same, right? Because they're flowing in a single path. So I'm going to declare, actually, I'm going to call this, sorry, let's go back. I'm going to call this B, and then I'm going to call this C, okay? So the change in voltage between A and B, right, is the same as the change in voltage across resistor R1, right? Okay. And that's going to be equal to I times R1, right, according to Ohm's law. The voltage difference, so now I'm here, I'm going to go from B to C, right, is going to be delta V of R2. It's going to be I times R2, and they share the same current. That's why we don't have to write a different current between them. Okay, the voltage difference between, so what happened is that, right, when you combine these 2 resistors together, right, you no longer have this middle piece anymore, right? This is actually point A, this is actually point C, right? R effective here, right? So delta V across A to C is the same thing as the voltage difference between R effective here, right? Also known as the equivalent. Okay. But one thing we know is that, well, if I have voltage A, jump to voltage B, jump to voltage C, right? A plus the change in voltage between A and B plus the change in voltage between B and C will equal to the voltage between A and C, right? So let's just make up some numbers just to make this a little simpler, right? So let's say voltage at A is 10 volts, voltage at B is 5 volts, voltage at C is 2 volts, right? So the jump from A to B, right? That's -5. Jump from B to C is -3, right? But the jump from A to C directly, right, is -8, right? So hopefully that makes sense, where the change in voltage from A to B plus the change in voltage from B to C is the same thing as the change in voltage directly from A to C. Okay. Now we can put all the stuff on the side here. So this, actually, I should finish this. This is the current times R effect, right? So I'm going to put in all this current version of it. So that's the A part. So I times R1, and then voltage difference between B and C is this piece here, I times R2. Okay, and R effective times R gives you the AC part, R effective, right? All of these I actually cancel out. So basically you get the equation that R effective, or R equivalent, is R1 plus R2. Okay. In the homework, you're going to do the same thing, where you can do the R3 also, but I'll save you and let you guys do that instead. So going back to our problem, okay, basically the entire VCC, right, you can combine all three of these resistors together, right, which is, I'm going to call that R effective, right, times whatever the current, because they all share the same current. Well, what's R effective in this case, which is R1 plus R2 plus R3, right, because there's three of them, times I. And then now, right, since we have 25, 50, 150, sorry, 25, 50, and 100, they add these up together, we get 175 ohm, right? And then we don't know what the current is, but we do know what the voltage is. Okay, so now we can calculate what the current is. Okay, the current is basically 5 volts divided by 175. 5 divided by 175, okay, is 0.029 amps. But remember, what we're going to do is we're going to write this in terms of milliamps. So it's 29 milliamp. Okay, that's the current. Okay, now we got the current, right? How do I calculate? So now I know, now we have to calculate the power dissipated. So power dissipated by resistor 1. So instead of trying to figure out what delta V across resistor 1 is, we can actually use the equation that doesn't need that. Remember, the current squared times the resistance actually gives you the power also. Okay, so the current square times R1 in this case, right, that tells you what the resistance is. So if you square 0.029 square times the resistance value of 1, which is 25, the power dissipated here is going to be 0.02 watts. Okay. Power dissipated by R2, since you have double the resistance, the same current, you're going to double the power dissipated. So that's going to be 0.0204 watts. Actually, I'm going to do one more sig fig. It's 21 watts. Okay, so this is going to be 42 watts. And then the power dissipated by R3, which is double of R2 once again, right? That's going to double again. So 84 watts. Hopefully that's not too confusing. Just taking a little shortcut to make these calculations much quicker. Okay. So that's how you calculate the power dissipated by each of the resistors. So next thing I want to cover real quick is that You can also have resistors in parallel meaning they actually go on two separate current paths. So this is going to be I1, I2, so be careful that they are different currents. And I'll let you guys derive this formula where the equivalent or the effective resistance is just the reciprocal of the combined resistance. Okay. What I want to finish up with is basically kind of take you through this new way of thinking about very similar stuff that we already thought about. Okay, where it's a resistor circuit still. You have a voltage source, and then you have two resistors. Okay, and what we're going to do is we're going to call this a voltage divider because it actually gives you some fraction of the voltage out, sorry, some fraction of V in at the output, which is actually going to be called V out. Okay, and this is one of the most important circuit. Actually, surprisingly, it looks very simple, but it's surprisingly useful circuit. So we really need to make sure that we understand how this circuit actually works. Okay, and this circuit is applicable to anything where you can connect a input to an output. Okay, and you know then if you have a circuit that has no input or output, it's kind of useless. So we don't want to make anything that's useless. Okay, so what I'm going to do is I'm going to derive this equation on how we can relate V out to V in. Okay, so once again, since this V out currently, when it's just set up like that, is not connected to anything yet. Okay, so there's no current flowing out here, right? No current, no I. Okay, so the only current flowing through it is from V in straight down through R1 and R2 into ground. Okay, and that's the only I we're going to be dealing with. Okay, so how do I figure out what is V out here? Okay, so one way you can do this is that, well, I have a V in here, right before resistor 1. Okay, and then I'm going to call this middle point V out, which is already done. And down here is actually ground, which is going to be 0, right? The voltage at ground, we're just going to set that to 0. Okay. Since the resistors, right, there's only one current, I should not have erased that, so I here. Okay, so V out, sorry, V in minus V out, meaning the difference in voltage between in and out between these two resistors obeys Ohm's law, right, which is going to be resistor 1 times the current. Okay, and then there's the second one, V out minus ground, which is 0. That's going to be R2 times I. Okay. What we want to do is have a relationship where V out is going to be some function of V in. Okay. So what we want to solve for here is actually, we don't want anything that has current in it because we know what R1 or R2 is, and we want to relate V in to V out. Okay, we want to get rid of this I. So what I'm going to do is I'm going to solve this equation for I and get rid of it. So this is actually, right, I is actually going to be V out divided by R2. Okay, I'm going to put that substitution in here. Okay, it's going to be equal to V out over R2. So this kind of gets into a kind of a complicated equation with multiple terms, right? R1 over R2 times V out. Okay, so I want to solve this equation for V out somehow. So I'm going to put all the V outs on the left hand side. Let's just do that. Okay, negative V out minus R1 R2 times V out, and then this goes on the right hand side. I need a little bit more space. Let's put that in there. Okay, I got to this point. I'm going to factor out this negative 1 right, and move it to the other side. Actually, in fact, I'm going to factor out negative V out. Let's just do that in multiple steps. In fact, I'll do this from left to right. A little bit easier to read, right? So what's left inside is 1 plus R1 plus over R2, right? That's equal to Vn. I'm going to try to add these together, right? If you want to add two fractions together, you have to have a common denominator, and the common denominator is actually R2 between them, because R2 over R2 is 1. Okay, so I'm going to multiply this -1 to the other side. Oh, forgot. Yeah, so when I do this, move this Vn over, I get a negative here also. So the -1 actually cancels out. Okay, so V out, if I solve this for V out, it's actually V in. Okay, I combine these two terms together. You get R2 over R1 plus R2. Okay. Hopefully I didn't skip too many steps. And basically this is the voltage divider equation, where the output you get here, okay, is proportional to Vn, of course. So if you double Vn, the output also doubles. But you multiply by this factor, R2 over R1 plus R2. Okay, and that's the voltage divider equation. Okay. So after watching this, I would literally just do it myself. Okay, and look at how the book does it, and then see how, and hopefully you see this as many times as possible. And that way, you get used to doing this, knowing this equation by heart, because we're going to use it a lot. Okay. Okay. What I'll wrap up with is actually give you a preview of the homework problem. So if you were to connect two of these voltage divider together, so this is one voltage divider here, and then you're basically connecting the output of voltage divider out as the input for voltage divider 2, right? What is V out here, right? And if we make all the R's the same, right? Because, right, if we make R the same here in this case, right, let's just erase R1 and R2, right? We will actually know what that ratio between V in and V out is, because if we make this R plus R, right, this will give you 2R, right? The R actually cancel out. You'll actually get 1/2 the V in voltage, right, if these two resistors are the same. So if we make combination of two separate voltage divider and put one of the outputs, so this will have a V in over 2 here, right? Maybe, right? And then we use that as the input for the second voltage divider. You would think this will be V in over 4, right? Because you're dividing the voltage twice, but it's not. Okay, and I'm going to have you guys calculate this carefully in the homework, and also explain it physically in the homework that you're going to turn in, and hopefully we figure out why that's the case, and this will be very important to know. All right, so that's all for the first lecture. Hopefully it's not too long, and then we'll see you in the second one.